let's go through calculating the commutation relationship for this total spin vector, this new operator we've met, and the operator to measure spin in the x direction. And a thought I had when doing this is I could imagine an entire YouTube channel just asking, does it commute? Because there was that really popular YouTube channel, maybe it's still popular, I don't know, called Does It Blend or Will It Blend? And they just put things in blenders and people liked watching that. So maybe if I just calculated the commutation relationship for a bunch of things, that could go viral. I don't know. So how would we do this? Well, that's going to be the first operator times the second operator minus the second operator times the first operator. And so we've written the operator up there. I've left it from before. We need to know what Sx is, and that's h bar over 2. And then this is the one with it on the off diagonals. Cool. So we have to just do out some matrix multiplication. And first, and I have to go in the right order, I'll pull down my coefficient from this, and now that identity matrix for spin 1/2 is just 1s on the diagonal, and then I have my Sx, 1s on the off diagonal. And then I'm going to subtract, going the opposite way, so 1s on the off diagonal for Sx, and then that 3 h bar over 2 squared, and it doesn't really matter how you've written this, there's other ways to write it, and then 1, 0, 0, 1. So we're going to bring out my 3, and now I have an h bar over 2 cubed, and now I'm doing my matrix multiplication. Okay, row times column, 1, 0, 0, 1 is 0, row column is going to be 1 times 1 is 1, 0 times 0 is 0. Okay, row times column is 1, row times column is 0. Okay, and now I'm subtracting from it 3 h bar over 2 cubed. And then, okay, so row times column is 0, row times column 0 times 0, 1 times 1, 1. Row times column is 1, row times column is 0. Okay, look at what has happened here. We in fact have the exact same thing subtracted from itself, right? Same coefficient up front, same matrix here. That equals 0. So just to make it as clear as possible, this relationship here, we would say these two operators commute. This means that you can know the measurement of these two things at the same time. And in a way, this is really telling you about the total spin. This is telling you about the direction of the spin. So that's it. There's kind of a little bit of a shortcut here, which I'll go into. But this is a case where the two operators commute. Something that is an eigenstate of this is also an eigenstate of that. And one thing you can think about here is if I have any quantum state, psi, and I apply this operator to it, well, that's the same thing as just saying 3 h bar over 2 squared identity matrix times psi. Well, identity matrix certainly gives you back your original state. And so effectively we can say then that this is going to have any state as its eigenstate, right? So anything here is not going to be disturbed by being measured by this. So effectively, the answer we get from here is always going to be, and I can call this, lambda if you want to think about it as an eigenvalue, but it is always going to result in 3 h bar squared over 4 for a spin 1/2 state. This number is telling you you have a spin 1/2 particle. And then this will give you plus or minus h bar over 2, telling you is it spin up or spin down. So of course we get the same number here all the time because these are all spin 1/2 particles. But then is it spin up or spin down? That isn't disturbing the fact that it's a spin 1/2 particle. So you wouldn't necessarily use that argument to say, well, okay, I don't have to do any of this math. Again, if the calculation is prove the commutation relationship or calculate what it is You have to do the math, but at the end we interpret it and go, well, of course they commute, because this is just telling you it's spin 1/2, at least in a spin 1/2 system. So I hope that that helps a little bit understand what this operator is. In fact, you can go through and calculate the commutation relationship with SY and SZ. They also work out to be 0. So this commutes with any of the individual directional operators, and that's useful and important, and again, a little bit obvious when this is just telling you that it's a spin 1/2 particle.